Okay, this is lesson number 1 of chapter 9, solving first degree trig equations. So just to give you an overview, in this chapter, we are going to solve both algebraically and graphically first and second degree trig equations, both in degree and radian mode, with a restricted domain and with an unrestricted domain that needs a general solution. So the unrestricted meaning that x could be anything, so when I declare my solution, I could have multiple solutions that extend indefinitely. And then we're going to prove trig identities using that formula sheet that you guys have. All of those trig identities, or all of those formulas that are written on there, we're going to be looking at those in this chapter. So if we look at a review from what we've done previously, if we wanted to solve for the following equations on a given domain. So if we had the equation sine x equals -1/2, and we wanted to solve this from 0 to 2 pi, how would we do that? Do you remember how we did that at the beginning of the last chapter? I first of all need to figure out what quadrants I should be in. So my sine value is negative. What quadrants does that put me in? 3 and 4. So then I want to determine my reference angle. So how do I determine the reference angle?
Take sine inverse.
Okay. So when I do that on my calculator, I go sine inverse 1/2. My calculator gives me this value. How can I convert that into an exact radian measurement?
So you like divide by pi and then times and then get a fraction.
Okay, so what's this fraction?
And 6.
So then what would my reference angle be?
Pi over 6.
Good job. So if I draw a quick sketch, that means reference angle pi over 6 in quadrant 4, reference angle pi over 6 in quadrant 3. So my x value in quadrant 3, how would I determine that?
Pi plus pi over 6.
Okay, and if I take pi and I add pi over 6, what do I get?
7 pi over 6.
Good job. And how do I calculate it in quadrant 4?
2 pi minus pi.
And what would that give me this time?
11 pi over 6.
Good. Okay, so let's look at B. B, I have the equation 3 secant x minus 5 equals 0. X this time is in degrees, and I want to solve this to the nearest degree. So what do I have to do first?
Get secant x by itself.
Okay, so how do I get secant x by itself? Add 5 to each side and then divide by 3. Okay, do I have a secant button on my calculator? So then what do I have to use?
1 over cos. Or you use your cos button.
I use my cos button. And my cos is the reciprocal of secant. So if secant is 5 over 3, what is cos going to be? 3 over 5. And then I repeat the same steps. So I'm going to give you a couple of minutes to repeat those steps. How do I go about solving this?
Well, it's quadrants 1 and 4.
Okay.
And then you find the reference angle.
Okay, so what's the reference angle?
53 degrees.
Okay. And then I always find it useful to draw a quick sketch so I can kind of get that visual of what I'm in each quadrant. So in quadrant 1, what would be my rotational angle? Okay. And what about quadrant 4?
307 degrees.
And how'd you get 307?
360 minus 50.
Good. Okay. So that's with the restricted domain. What happens if we don't restrict the domain? That's the general solution, and that's what we're going to look at for part of this, for part of today and part of tomorrow. So it says, consider the equation sine x equals negative 1/2. That's the first class example. So use the following graphical method to estimate the solution to the equation on the following domain. So use this window setting and graph y1, and then determine the x-intercepts. So again, I'm going to give you a couple of minutes to work on that. When you graph this, what you will get is you will get this graph that ends up going through at this point and at this point. It starts here. That seem about right? And those two intersection points are the 7 pi over 6 and 11 pi over 6. And by using pi over 6 as my scale marker, I can actually count that out. So now what I want you to do is adjust the window settings. Don't change the equation, but adjust the window settings. So instead of going from 0 to 2 pi, you're going from negative 2 pi to 4 pi. And then sketch that in. So if I go to sketch this one, what do you notice happens? How many intersection points do you get?
6.
So I get this graph that kind of goes like this. Something like that, right? So what are all these intersection points? Okay, so that's your homework. Find out what those intersection points are
Cole Tucker,
as
can you come to the office, please?
exact
Cole Tucker?
values.
Oh, I did that. Oh.
Okay, so
Space.
yesterday we left off with looking at the sine x equals negative 1/2 equation. So we made it into the equation of sine x plus 1/2. We looked at a domain from 0 to 2 pi, and then what I left you with was exploring the domain from negative 2 pi to 4 pi, and determining the x-intercepts as exact values. So what did you get for exact values?
Negative 5 pi over 6. Negative pi over 6. 7 pi over 6. 11 pi over 6. 19 pi over 6. And 23 pi over 6.
Okay. Now, what you'll notice is that I have two sets of answers. I have this first set, and then I have this second set.
Mrs. Hanson, line 1, please. Mrs. Hanson, line 1.
And the first set, if I take my solution that I got up above from 0 to 2 pi, this 7 pi plus 6, how can I go from 7 pi over 6 to 23 pi over 6? Or sorry, not to 23, to 19 pi over 6. Add 2 pi. And how can I go from 7 pi to negative 5 pi? Subtract 2 pi. So this first set of negative 5 pi over 6 and 7 pi over 6 and 19 pi over 6 are angles that differ by a multiple of 2 pi. And then the second set, negative pi over 6, 11 pi over 6, and 23 pi over 6 are the same. they differ by a multiple of 2 pi. So it says if I change the domain, instead of going from negative 2 pi, I now go from negative 4 pi. And instead of going from 4 pi, I go to 6 pi. Could I come up with 2 more solutions for each set? So if I look at the first set, if I subtract a 2 pi from this negative 5 pi over 6, where would I end up at?
Negative 17 pi over 6.
And if I add 2 pi to the 19 pi over 6, and then I can do the same thing with the second set. If I take negative pi over 6 and I subtract 2 pi, what would I get?
Negative 13 pi over 6.
And if I took 23 pi over 6 and added 2 pi, I would get
35.
and I could keep doing this indefinitely. I could just keep adding multiples of 2 pi. So what we come up with is we come up with a general solution. And the general solution says, take the solution I get in the first domain, the 0 to 2 pi domain. That's my 7 pi over 6. And from that 7 pi over 6, I can get all the rest of them, the negative 5 pi over 6, negative 17 pi over 6, the 19 pi, and the 31 pi, by adding multiples of 2 pi. And then I also have my other solution, which was the 11 pi over 6. And again, to get those ones that were in red, or the other 2 examples that we got in D, I can take the 11 pi over 6 and add multiples of 2 pi. My condition is that n has to be an integer. So if n is equal to 1, then it's adding 2 pi. If n is equal to negative 1, it's subtracting a 2 pi. If it's negative 2, it's subtracting 2 pi, or 4 pi, and so on. Okay? Now, the solution that we got in the last example can also be obtained by using intersections. So what we did is we found the zeros. We wrote it as a y1 equation only, but I could do this as a y1, y2, where I let y1 be equal to sine x, and I let y2 be equal to negative 1/2. And if I did that, I would get this horizontal line that goes through negative 1/2. And then what I would be looking at would be all these intersection points and what the values were above. So there's my negative pi over 6, my negative 5 pi over 6, 7 pi over 6, 11 pi over 6, and so on. Now, the reason why these answers differ, there's my first set, and here's my second set. The reason why they differ by 2 pi is because that's the period of sine. So every 2 pi, that sine graph repeats itself. Okay? So then we've got a graphical approach to finding the general solution. So what I can do is I can use the graphing calculator, either the intersect method, which means I have 2 graphs, y1 and y2, or the zero method, which is when I have 1 graph. What you want to do is you want to solve the equation where the domain is 1 period, which is for a sine graph is going to be from 0 to 2 pi. A cos graph would be 0 to 2 pi. And if I had a tan graph, what would be one period for a tan graph? 0 to pi. And then what I do is determine the general solution by adding multiples of that period to the solution I got in step 1. So if we look at class example number 1, it says solve the equation cos x minus 0.75 equals 0, where x is a real number using 2 different graphical approaches. Give the answers to the nearest hundredth of a radian. So they're not asking you to do this in exact measures. They want you to do this as a decimal. So if we look at doing the 0 method first, that means I would let y1 be equal to cos x minus 0.75. So I want to make sure that my graph, first of all, that I'm in radian mode. Secondly, I go to my window settings. I want to go from 0 to 2 pi, and I can type in 2 pi, and the minute I press enter, it'll change it into a decimal. And then if I look at my scale here, I've got 6 tick marks. So my scale is a pi over 6, which again, I can write it out as pi over 6, but when I press enter, it's going to change it to the decimal equivalent. And then for my min and my max for my y values, well, this 0.75, that's my D, that's my midline. So that's moved the graph down 3/4, and then my amplitude is a 1. So if I went from 2 to 2, -2 to +2, that would probably be plenty, and then had a scale of 0.5s. Y equals cos x minus 0.75, and there's my graph. So if I sketch what this graph looks like, it appears that it's going it cuts through right after the first tick mark and kind of right before the second last tick mark. So something like that, and then I find out what those 2 0 values are. So second calc, 0. Again, the left bound means the left side of the 0. So that would be making sure I'm in the positive y values. And then I need to go to the right side, which would be the negative y values. And I get 0.7227. So x equals 0.7227. And then I do the same thing to get the other 0. What do I get for the other 0? So then my general solution would be to take that first 0, and we're going to round it to the nearest hundredth, so 0.72, and then add multiples of the period, which is 2 pi. And then my second solution, 5.56, rounded to the nearest hundredth, plus multiples of 2 pi. Condition being that n has to be an integer. Okay. So the second way of doing this is the intersection method. And that's where I would have the 2 graphs. So I would take my cos x minus 0.75 equals 0, and I would isolate cos x. And I would get that cos x equals 0.75. So y1 would equal cos x, and y2 would equal 0.75. So there would be my cos x graph. And then my 0.75 would look something like this. And I would be looking for these two intersection points. And what do you think those two intersection points would be?
0.72 and 5.56.
They'd be the same thing as they were before. It's just doing this another way. So I'm not going to go into a lot more detail on that one. So that's looking at this graphically. If we have to do this algebraically, it's usually because we're asked to find the exact value. So again, it's going to be the same thing. You're going to solve this for one period of the domain, and then you're going to extend it by adding multiples of the period. So class example number 2 says use an algebraic procedure to find the general solution of the equation 2 cos x minus root 3 equals 0, where x is in radian measure. So what would I do with this equation to begin with? In order to solve this, what do I have to do?
Isolate cos x.
Isolate cos x. So how do I isolate cos x?
I'd probably add root 3 first.
Move root 3 to the other side, and then what?
Divide by 2.
So I get cos x equals root 3 over 2. Then what do I do?
Cos inverse root 3 over 2.
Okay, so I find the cos inverse. What is that going to give me? Reference angle. Okay, so cos inverse. So cos inverse root 3 over 2 How do I make that an exact measurement? Because it's this decimal right now. Divide by pi. And I get that 0.16 repeating, which is what is a fraction? 1/6. So the reference angle would be pi over 6.
When I type like cos root 3 over 2, I get like an error on my calculator. For some reason.
Make sure you put brackets after the root 3. Yeah. So what's happening? The square root of 3 divided by 2?
It's like square root of 3 halves.
Right. And that gives me a number that's actually greater than 1, and I can't take the cos of a number greater than 1. Okay? Why can't I take the cos of a number greater than 1? Just try it right now. Go cos inverse 1.2. And what do you get? So that means it doesn't exist. Why doesn't it exist?
It's not between 0 and 2 pi.
What's the ratio, or what's the formula for cos? Cos equals what? And in a triangle, what can you tell me about the hypotenuse?
So is the biggest side.
Always the biggest side, so I'm always going to get a proper fraction. I'm always going to get a number that is between 0 and 1 or 0 and negative 1. Okay? Okay, so I have my reference angle. How does that help me find my solutions in the first period? What else do I need to know about?
You have to determine what quadrants.
Okay, so what quadrants is cos in?
Quadrant 1 and quadrant
1 and 4. Okay, so then I'd have pi over 6 and pi over 6 in those two quadrants. So in the first quadrant, what is x equal to? Pi over 6. And then I can add multiples of 2 pi n to get my general solution. In quadrant 4, what is x equal to? 11 pi over 6. So 2 pi minus pi over 6. I get 11 pi over 6, and then I add my multiples of 2 pi with the condition that n is an integer. Okay. Let's look at sine x equals 0. How would I do this one? What's my reference angle? Zero. Okay. In this case, 0 is neither positive or negative, so I actually have to consider all 4 quadrants. In quadrant 1, my angle would be 0. In quadrant 2, my angle would be 180. It's 180 minus pi, which would, or sorry, pi minus 0, which would be pi. What would it be in quadrant 3? Pi again, because this time it's pi plus the reference angle. And what about quadrant 4? So my solution in the first rotation, or in the first domain, is is pi and 2 pi. So if I was to look at this as a general solution, I have pi plus 2 pi n, and I have 2 pi plus 2 pi n. Can I combine this at all?
Could you just add them together?
In a sense, I could just, this right here would give me 3 pi, and then 3 pi, 5 pi, 7 pi, 9 pi. This is going to give me 2 pi, 4 pi, 6 pi, 8 pi. So I have pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. Simply put, I have multiples of pi n. So sometimes you can actually combine the solutions, or combine the two general solutions to create one. Okay, what if cos x equals 0? What's my reference angle?
Well, I got 1.5707.
Okay, so divide that by pi, and what do you get?
Pi over 2.
Pi over 2. And again, because we're dealing with 0, I have to deal with all 4 quadrants. So in quadrant 1, x would equal
Pi over 2. I mean pi over 2.
pi over 2. In the second quadrant would be pi minus pi over 2, which is pi over 2. In quadrant 3, it is pi plus pi over 2. over 2. And in quadrant 4, it's 2 pi minus pi over 2. So 3 pi over 2. So these are my two solutions. If I start adding multiples of 2 pi, another way to picture this is if I looked on my coordinate grid. I have a solution here and a solution here. So if I start adding multiples of 2 pi, from this solution I go around and I go around and I go around and I go around, and the same thing with down here. But these two solutions only differ by how much? By pi. So I can start off at my pi over 2 and add multiples of pi again. So when can I combine my general solutions? I can combine my general solutions when they differ by something like pi. If I look up at this one right here, they don't differ by pi. So it's not as easy, and you can't combine the two solutions. This one right here, I have pi and 2 pi. They differ by pi, so I can just keep adding multiples of pi. Okay. The last one just deals with a restricted domain. So for example, if I have 2 sine x equals root 2, and I restrict the domain to be from 360 degrees to 720 degrees. How would I solve that? So let's start with the same steps that we did before. What was the first thing that we did? Move everything to the other side. So we isolate sine x. So if we isolate sine x, we would get that sine x equals what? Okay. Then what would I do?
Determine the quadrant.
Okay, so what quadrants would sine be?
1 and 2.
Okay. Now what? Okay. When I find my reference angle, what do I have to make sure of?
That the square root of 2 is in brackets.
That the square root of 2 is in brackets. What else do I have to make sure of? Look at my domain. You have to be in degree mode. Yeah. For this portion of your diploma, you will switch back and forth from degree to radian mode consistently. So what did you get for a reference angle? 45 degrees. So in quadrant 1, that's going to be 45 degrees. What is it going to be in quadrant 2? But my solution for x has to be between 360 and 720 degrees. So it basically has to be another rotation around. So a full rotation is 360 degrees. So if I add 360 degrees to that equation I got, or sorry, that angle I had in quadrant 1, where do I end up at?
405 degrees.
And then if I add 360 to the 135, I get
490.
good. Okay, last question. Square root of 3 cotangent x plus 1 equals 0. And the domain is from negative pi to pi. Or sorry, negative pi to 0. So what would I do first? Okay, so if I isolate cotangent, what do I get?
-1 over.
Okay,
And you could change it to like inverse tangent.
so when I change it to tangent, if cotangent x equals -1 over root 3, what does tangent x equal?
-√3.
And do I need to put it over 1?
Um,
Okay, so tangent would equal -√3. Okay? Now what?
determine quadrants and
Okay, so what quadrant is tan in?
well, Q2 and Q.
Okay. But remember, I have to be from -pi to 0. So -pi to 0 is actually going counterclockwise. So which quadrant would I have to be in?
Just in quadrant.
Just in quadrant 4. So I don't need quadrant 2. Okay, so let's find the reference angle. So determine the reference angle for me. When you have it, shout it out. Oh, I think I've got this part wrong here. Don't worry about the quadrant 2 and 4 for now. Still find my reference angle for me though. Pi over 3. Okay. My period for tangent is what? Pi. Period is pi. So if I was looking at a general solution, I would take this reference angle and I would add multiples of pi. Or subtract multiples of pi. So if I went pi over 3 and I subtracted pi, what would I get? Oh, wait a minute. I still have that right. Sorry, I'm confusing myself with my notes. So we were right to eliminate quadrant 2. So I would be looking at quadrant 4. So if my reference angle is pi over 3, and I'm going from 0 to -pi, this angle would now become negative pi over 3. Because I'm looking at this rotational angle, not this one. You see the difference? So I'm looking at the rotational angle that's going clockwise, which is a negative angle. And that fits into the domain. Okay, the questions I have for you are questions 3 and 4.